Multi-cloud applications are becoming more common, and by default, their traffic flows over the internet. However, when it comes to business-critical applications, there are three major challenges when using the internet as transport. Privacy and security. The internet is neither private nor secure, and no amount of tunneling fundamentally changes that fact. Second is performance. Application performance can be impacted by many factors, but with networking, it's really the consistency that matters. Time and variance of transmission greatly impacts performance, and the internet transport is just best effort and just hasn't got any performance guarantees. Then we need to consider cost efficiency. Cloud network consumption is designed for delivering applications to users, but when you're faced with a lot of workflows that are multi-cloud in nature, egress costs can become a real factor. Previously, getting around internet connectivity required you to turn to traditional telco solutions. You have to commit for long term and in many cases wait for weeks or months just to get started. However, there is a newer, private and secure way to connect your multi-cloud workflows, which gives you predictable high performance, in other words, lower latency at a predictable cost. For information on how we address privacy, security and cloud egress costs, please visit us at PacketFabric.com. In this demo though, I'm going to show you how PacketFabric enhances multi-cloud application performance by 225% in this demonstration, and show you how easy it is to provision PacketFabric's on-demand private network. Before we discuss the demo, let's start with a shared definition of bandwidth and latency. Bandwidth is how many units of data can be moved per unit of time, and latency is the length of time it takes to move 1 unit of data. For highly transactional systems like Apache Kafka, we believe that latency matters more than raw bandwidth and has a real impact on performance in a multi-cloud deployment. See, everything we do online involves transactions. A transaction can be as simple as opening a connection, yet usually involves the exchange of a simple message. When lots of these transactions occur in a continuous fashion, it's known as streaming. What if by simply guaranteeing the latency, you could more than double your transactional throughput? And why does that matter? Well, imagine a business intelligence system that can either reach a decision faster or make a higher probability decision in the same time because it received twice as much data. So now for the demo. We'll measure the throughput of Kafka streaming processing between AWS and Azure when connected via the internet, and then compare the throughput when connected via PacketFabric's cloud router. Now, PacketFabric's cloud router can be provisioned in minutes with a global reach and connections ranging from as low as 50 megabits up to 100 gigabits per second connections. It utilizes private, secure transport and is deployed using a distributed architecture across PacketFabric's global network fabric for consistently high performance. This test environment is designed simply so you can replicate the results. In the following topology, we'll deploy AWS's managed streaming service for Kafka, or MSK. Kafka is provided by services known as brokers. The brokers manage topics. A topic is analogous to a mailbox. A Kafka producer is created in Azure on a virtual machine using some open source data pipelining software. The Kafka producers send messages or mail via collections known as batches. How fast the producer can stuff the mailbox or how many batches per second can be delivered over an extended period of time is the measurement by which we'll compare the two services. To create a more real-world environment, background noise will also simultaneously be injected. Information about the entire setup, step by step, is available in a forthcoming blog. On AWS, the Getting Started Using Amazon MSK is instrumental and was used as a basis for this demo. The client VM, created as part of the AWS guide, was used as the iPerf3 server end. On Azure, there are 2 VMs in the same VNet. In one, I'm using the iPerf3 traffic generation tool to create this background noise up to 800 megabits per second. In the other VM, I'm running ETL or extract, transform, and load pipelines from StreamSets data collector, which has a Kafka producer configured to point to an AWS MSK broker's private IP address, along with the corresponding topic created for the AWS MSK guide. When started, the Kafka producers send approximately 150 megabits per second, giving a total of 950 megabits per second for our test. This is below the 1 gigabit per second PacketFabric circuit speed, as well as below the 1.25 gigabits capacity limit for site-to-site VPN. Therefore, we are not testing bandwidth per se, but latency. As shown in the graph, the cloud router sees the 950 megabits per second throughput. Summarizing the results, after approximately a 25-minute test run, the PacketFabric cloud router solution has 225% more throughput or goodput over the Internet VPN solution. Measuring latency using ping, we can see the latency for ICMP packets for the round trip. As can be seen, this correlates directly with the increase in throughput for our transactional system, as we'd expect with the RTT or round trip time average for the VPN being approximately 210% over the PacketFabric cloud router. Latency directly impacts the throughput and goodput of transactional systems in multi-cloud environments. Let's briefly show the corresponding cloud configuration that match each section of the diagram. For details on setting up the performance tools and site-to-site VPN, please refer to our forthcoming AWS blog. Now let's show how easy and simple it is to configure this high-performance solution with PacketFabric. You'll find extensive and easy-to-read documentation available at docs.packetfabric.com. Everything you need to know about the PacketFabric Cloud Router service is described in our documentation. From prerequisites, field descriptions, and detailed how-to guides, you'll find this an invaluable reference for all our services. For this demo, you will be starting with creating a cloud router, add AWS Direct Connect to a cloud router, including configuring BGP, add an Azure Express Route connection to a cloud router, and also including configuring BGP. Assuming IP addresses for the network like so, after following the documentation as just described, the cloud router configuration for AWS appears like so. The connection, transit VIF, Direct Connect Gateway, and Transit Gateway. The transit attachment to the same VPC as used in the AWS MSK guide, and shows a routing table in AWS with the routes from Azure, and our cloud router concurs.